Hello. So today we are going to talk about this heat flow equation that I'm presenting over here in the board. Over here this symbol, it is the Laplacian operator. If you remember that, then know that del square it's equal to del 2 del x squared plus del 2 del y squared plus del 2 del z squared. So over here what we are considering, it is the general heat flow equation. That is when three coordinates are involved, space coordinates, three of them are involved, and also there is the time factor. Because if you think about it, okay, suppose you are having this square box and you supply heat to one corner of it. You know that heat will flow throughout the box, but how much? Okay, that is described by this equation. Okay, so what we are saying over here is, okay, if you move along this direction, okay, if you consider any time, any instant of time, suppose maybe after 1 second, you will notice that this portion here will have different heat from portion here, okay, different temperatures, and similarly different temperature from over here, and similarly in any portion of the box. Okay, so that is why the heat or the temperature depends upon the three variables x, y, and z, okay, because it is different for different positions. Similarly, if you consider 2 seconds, this heat that we were taking at this temperature that we are considering in 1 second, it will be different, right, from after 2 seconds. So that's why it also depends on time. That is why over here we are having three coordinates, and also we are having the time factor. But okay, what can happen is sometimes we can consider more specific cases. The specific cases that we are interested in this session will be about one-dimensional heat flow. When we are talking about one-dimensional heat flow, it means that only one space coordinate will take place. Of course, time will also be there. So we are considering only one x, okay, the space coordinate x, and the time factor t. That is why these terms will not be involved. So over here del square will take the form del 2 del x squared. That is why for one-dimensional heat flow equation, we will be having this general equation, del square u del x square equal 1 by alpha square del u del t. Okay, so this one is for the one-dimensional. As examples for one-dimensional heat flow, you can think about things like this. Okay, suppose you are having a long rod and you are heating it, okay, and you are thinking that, okay, the heat cannot go to the surroundings. Okay, so that is why heat can only flow in this direction, or you can even flow it from this direction depending on the temperature difference. Okay, so over here we are considering one-dimensional heat flow. Okay, so when you are having a long rod, okay, which is infinitely, the diameter doesn't play too much of a role, then this is an example of one-dimensional heat flow. Or another example that you can think of, okay, you can even have some kind of a slab, okay, where instead of heating one corner, of course we know that if we heat only one corner of it, then the heat from here will be different, let's say, from the heat over here, okay, or from the heat at this point. But instead of heating only one corner, what we will do, we can heat this whole side. If we heat this whole side, with a constant temperature, then heat will only flow in one direction. Okay, so heat will only flow in one direction because we are maintaining this constant heat source that acts throughout this whole site. Okay, again, I repeat, it is different from the case when we were heating only one corner of this slab. Okay, so I hope you are getting it now. Similarly, if we have a box, okay, if we heat one face, okay, the whole face at a constant temperature, then in that case also the heat flow will be one dimensional, okay, because it will only be flowing in this direction. It cannot flow in this direction because it is the same heat. It is the same temperature. Heat flows only when there is a difference in temperature. I hope you remember that. Okay. So what are the types of problems that we will encounter in this one-dimensional heat flow? Okay, there are these types of problems which we call as boundary problems and initial value problems. Okay, so just by thinking about it, okay, so suppose we are having this rod of length L. Okay, so over here the position is x is equal to 0 because the whole length is L and x equal to L. What exactly are we talking about when we are talking about initial value problems? Is actually when the time is 0. Okay, and what about boundary problems? Boundary problems, they are the problems when, okay, these ends, okay, at the boundary you have different heat, okay, different heats at the boundary, okay, different temperature at the boundaries, okay, as you will see, okay, when we are doing examples. But first, okay, initial value problems and boundary problems, they are very important when we are studying partial differential equations, because as you see, this equation is nothing but a partial differential equation. Okay, so boundary problems and initial value problems are important when we are studying PDEs. And over here, the boundary problems, okay, usually what we will do is, okay, because u, it depends on x and on t, right? So we can say that u will be a function, it will depend on x as well as t. For boundary problems, okay, what is specified? We are specifying the heat, okay, or the temperature. We are specifying the temperature at the end points. So when x is 0, so u0t, maybe you are having some value, and u lt is also having some value. And initial value problem is u, when the time is 0, u x 0, okay, because the function is a function of x and t, okay, so u x 0. I hope that is clear. Okay, but sometimes initial value problems and boundary problems in this heat flow equation can be described in some other way. Okay, over here what we are doing, initial value problem ux0, so we are specifying the heat of this rod initially at each and every point. Okay, we did not specify what the value of x is. Okay, sometimes, okay, because it is the initial value, we use u naught x0. Okay, again I repeat, we are specifying the temperature of each and every point of this rod at time equal to 0. Okay. So with this being said, okay, let us just go ahead to an example. Solve the heat flow equation. Okay, for this case, heat flow derivative 1 by alpha square W del T, as we have seen. So we are going to solve this one for these conditions. Okay, the initial conditions U00 is equal to 10, okay, 10 units. UL0 is equal to 50, and the boundary conditions U0T is equal to 30, ULT is equal to 100. So actually what this question is saying is, initially before any experiment has started or something, what we are doing, we are keeping this end of the rod at temperature 10, okay, and this one at 50. Okay, and usually what we find that in most of the problems that we are considering is that initially we are having a steady condition. Okay, but if you remember that when we have to describe initial conditions, we have to describe for this whole section, not just for the endpoints. But over here, we are describing the initial conditions only for the endpoints. But the initial conditions, we will have to find out for each and every point. Because just think about it. Okay, initially what you were doing before the experiment has started, you have kept this one, the end, at 50, and the temperature of this one, let's say 50. So there will be some heat flow initially also. But because it has arrived at a steady state, okay, let us think about this. Okay, so temperature, okay, I will plot it upwards, and this is the rod, okay, the position, specifying the position. So initially it was at the temperature 10, and L was at a temperature 50. Okay, so you were keeping this rod in these conditions, and it has achieved a steady state. When it has achieved a steady state, just think about it. Okay, since you are keeping this one at 10 and this one at 50, what will be the position of this point over here? Will it be greater than 10, greater than 50, less than 50, less than 10? Okay, if you think about it, it makes sense that the temperature of this point will be somewhere between 10 and 50. Okay, so let's say somewhere here. Okay, if we were to plot the temperature. Similarly, this point over here, okay, it will be closer to 50, right? Since this one is hotter and this one is colder, so you will expect that if you plot the temperature of all of these points, each and every point, okay, you will achieve something like that looks like this. Okay, over here we are using a straight line, but it may as well be, okay, some other curves. Okay, but you get an idea that the temperature will increase like this along this length L. Okay, because this one is at a colder temperature, this one is at a high temperature, so we will expect that the temperature will increase in this way. Okay, but we don't know for now whether it is a straight line or curves that looks like this. Okay, but what we will do, we will prove that in the initial steady state, okay, in fact, in any steady state, the temperature, which no longer depends on time. since we have arrived at a steady state, okay, so the temperature no longer depends on time, it will only depend on a position. So we will show that for the steady state, or in fact it was proven already that for the steady state, the temperature, when the position varies, it will be linear, that it will be a straight line like this. Okay, so these curves won't come into the picture. Okay, we will do that. Okay, why exactly are we doing it? Because as I said, we want that the initial steady condition, we want to describe it for the whole rod, not only for the endpoints. Okay, so over here we are given u00, ul0. What do we have to do? We have to find ux0. Okay, or sometimes u0 because it is initial. Okay, but it's just a matter of notation. Okay, but the main purpose is finding this ux0. Okay, let us first do that. Only then can we proceed further. Okay, so let us first find the initial steady state condition. Okay, so since okay, so solution, let u0 be the initial steady state condition, and this initial steady state condition no longer depends on time. So if you substitute it over here, okay, del u del t, it will be equal to 0, or del u0 del t will be equal to 0 because it no longer depends on time. So we will be having del to u del x squared equal 0. Now what we will do, okay, so remember that u0 was depending on x and t only, x and t, but u0 no longer depends on t, so it only depends on x. So this one, instead of a partial derivative, because we are having only two variables, now we can think of it now as a total derivative. Okay, again we can proceed directly, okay, but just to be clear, we can easily replace this partial derivative with the total derivative. So if you solve this differential equation, you will see that u0 will be of the form, okay, let's write it as a0x plus b0, which we can easily tell that it is linear. Okay, this one, it's of the form of a line, right? It is an equation of a line, ax plus b, y equal ax plus b. So that is why we just proved that u0, okay, it will be a linear function. Okay, so that's why we will be having something that looks like that, okay, for this case. Okay, and a0 and b0, they are constants that we have to find. How will we find them? By using these conditions at the boundary. Okay, the initial conditions was also given for the boundary, so let us use those conditions. Okay, let us write it here. For x equal to 0, u0 only depends on x, so when x is equal to 0, for x equal to 0, you will be having u0 equal b0. Okay, for x equal to 0, u0, it will be equal to 10. So substituted in this equation, you will be having 10 equal 0 plus b0, which gives us that b0 will be equal to 10. Now use this condition ul0 for x equal L, u0, it will be equal to 50. So again substitute it over here, but now b0 is equal to 10. So 50 equal a0. A0 will be, we have to find out how much it is, and 10. Okay, so a0, and this one is L. So a0, it will be equal to 40 by L. Okay, so the initial condition, what we will do now, okay, we will find the initial condition, hence the initial condition is u naught x 0 when the time is 0. It will be of the form a naught x plus b, but a naught is 40 by L. So 40 by L, x plus b naught plus 10. I hope that is clear. Next, what will we do? Okay. What exactly are we interested? We were interested in finding uxt. Uxt describes the heat or the temperature, the temperature at different positions x at different time t. Okay, but if you remember now, so the initial conditions have already been used here. We won't use them anymore. Now we are only interested in the boundary conditions, which I will write again here. So we were having 0t equal 30, u L t equal 100. So these are the boundary conditions. Now we want x and t. So now what has taken place right now? Okay, so initially the rod was maintained. The rod was maintained at 10 and 50. But then, okay, we changed the temperature at these ends. Okay, the temperature at these ends are now 30 and 100. After changing from 30 to 100, we will watch what happens. So there will be some heat flow because now we have changed. Okay, initially this was steady. Okay, it was no longer changing for when we were having the initial steady state condition, okay, because it was steady. But now what we did, we have changed the temperatures at the ends to 30 and 100. So again there will be heat flow. So what we are interested in, again in finding uxt. Okay, but take this one as a rule for now, that when we are having non-homogeneous boundary conditions, we have to do something else first. Okay, so how do we know that these boundary conditions are non-homogeneous? If you remember, this one is not equal to 0 and this one is not equal to 0. If any of the boundary conditions are not equal to 0, then you can say that they are non-homogeneous. Okay. So what will we do then? If it is non-homogeneous, we can proceed in the following steps. Okay, because we want a situation where the where the boundary conditions are homogeneous. That will make our solution easier to find. Okay. So what can we do? Okay, we can think of it in this way. After letting the experiment go, okay, after changing it to 30, okay, we let the rod to achieve a steady state again. So there was an initial steady state and there will be a final steady state, okay, where we will describe the temperature in the rod by UF. Okay, so there will be a final steady state UF. After all the heat flow has stopped, okay, it will again be steady. Okay, what we are interested in, okay, we will find the steady state. In fact, to achieve the solution, okay, for non-homogeneous boundary conditions, we will write like this. Okay, we want to find uxt, so let uxt equal vxt plus the final steady state. But again, the final steady state, because it is steady, it will no longer depend on time. So that's why I can write it as ufx. First, let us find what ufx is, because it is steady. Okay, so now we will finding ufx. Again, we will substitute it in the heat flow equation and we will use the boundary conditions. Now, how do we know that u of x will satisfy the boundary conditions? Because, okay, because after this experiment has started again, we were keeping this one at 30 and 100. Okay, so this was allowed to achieve that steady condition. Even during the steady condition, this end of the rod is still at 30 and this end of the rod is still at 100. So we can still use the boundary conditions even for the steady state. So how do we exactly find this one? We can substitute this one in the original heat flow equation. Okay, del u del x squared equal, but now it's del f 1 by alpha squared del uf del t. We can substitute this one over here, but now del uf del t, again it is 0 because it is steady. So we will be getting the same thing, del d2 uf dx squared equal to 0. Again, we have changed it into a total derivative because it no longer depends on time. And there is only one other variable, which is x. So if we solve this one again, we will be having something that looks like this, uf equal, again it will be linear. It will be linear because every time in the steady state, okay, just like I had explained, in the steady state, the temperature will be linear, okay, throughout the rod. Okay, what I'm saying, so we were keeping this rod at 30 and this one at 100 even during the steady state. So you can expect that the temperature will maybe increase like this. Okay, so now what do we have to do? We have to find AF and BF by using the boundary conditions, because again the boundary conditions, it's still satisfied by UF. Okay, so when x equal 0, UF is 30, x equal L, UF is 100. So we can substitute that one over here, x equal to 0, so BF will be equal to 30. And when x equal to L, so you will be having AF, okay, UF will be 100, 100 minus 30 will give you 70, 70 by L. Okay, so we can find UF like this, and we will be having UF. Okay, so we had find U naught, we had find UF x. UF x, it will now be equal to 70 by L x plus 30. Okay, so now we have found the initial steady state and then the final steady state. Now we just need to find the temperature in between. Okay, what will we do? Okay, so remember that our original heat flow equation was something like this. Del 2u del x squared, it's equal to 1 by alpha squared del u del t. But now remember that u, we have written it as v plus uf. Okay, so let's substitute it here. Okay, so what will we be getting? V plus f uf by del x squared 1 by alpha squared v plus uf. Okay, and then remember that, sorry, okay, del t v plus uf, but remember that del 2, okay, so you can actually split this one, and the second order derivative partially with respect to x of uf, it's 0, so plus 0. Similarly over here we'll be having 1 by alpha squared del v del t, because del t of uf will be 0 again. Okay, so we'll be having this. What actually do we do after getting something that looks like this? Okay, so what can we do now? This is the method for finding the solution. Okay, we can write v, okay, because v, it is a function of x and t. It depends on the position as well as the time. we can write v equal f t, capital T, where f depends on x only, and t depends on t only. After doing this, okay, you will see okay, now substituted over here in this equation, you will be having del 2 del x square, v is ft, 1 by alpha square del t of ft. So we will be having this. But f now depends on t only. F depends on x only and t depends on t only. So what can we do? If we take the partial derivative, t will be treated as a constant because it depends on t only. So we will actually have something that looks like this. Similarly, here f does not depend on t, so you can take it outside. It behaves as a constant with respect to t. So we'll be having this. Next, what will we do? We can divide the whole thing by ft. Divide by ft, we'll be having 1 by f del to f del x squared equal 1 by alpha square t del t del t. By doing this, what actually did we achieve? We have separated, this is a space part, okay, it depends only on the only on x, and this one depends only on t, okay, because f only depends on x and t only depends on t, okay, alpha is a constant. So what can we do now? We can set both of these to be equal to minus k squared, okay, and separation constant, which we call. After this, we will solve this one is equal to minus k squared, and again solve this one equal to minus k squared. Okay, so let us first solve this time part equal to minus k squared. Okay, what will we get? Okay, I'll do it over here. Okay, so then you will be having, but again, since everything now it is okay, depends on t only, right? So we can easily replace del by dt, okay, just to make it clear that now it has behaved as a total derivative, okay, because we are having no longer variables, no other variables in this part of the equation. So for minus k squared, we can split the variables. So dt by t equal to minus alpha square k square dt. And then what can we do? We can integrate them. Integrate both sides. So you will be having log t, and over here you will be having alpha square k square t. And then you will also be having a constant, which I will be denoting by log c1. Okay, so log t by c1 is equal to minus alpha square k square t, which you know. Okay, so t, it will be equal to c1 e minus alpha square k square t. Okay, so this is when solving this one is equal to minus k square. Next, what I will do here separately is solve this one equal to minus k square. Okay, which I will do now. So this one again, now it has behaved as a total derivative because there are no other variables. d to f dx squared equal minus k squared. So we will be having d to f dx squared plus k squared f will be equal to 0. Okay, so k, it can be equal to 0, less than 0, or greater than 0. Okay, we can consider all those cases. Okay, but over here, what we will be interested in, okay, is this solution. Okay, so if you see this one, it is a second order differential equation, and it will give the solution like this. F, okay, solve it as a second order differential equation. Okay, find the auxiliary equation. Okay, and it is homogeneous because it's equal to 0. So after doing all that, you will be having that F will be equal to A1 cos kx plus B1 sine kx. And over here, I am omitting the other cases, which I will explain in another video. Okay, but for now, let us just take this solution. Okay. So after getting this one, but remember that initially we had substituted V equal Ft, right? So now we just multiply F and T. I will write it here. Now, V, it will be equal to Ft. So you will be getting A1 cos kx plus B1 sine kx times T, C1 e minus alpha squared k squared T. So you'll be having this one. Okay, so A1, C1, it will be a constant, okay? Multiply this constant over here. So A1 and C1, it is still a constant. I can denote it with A cos kx. B1, C1, again, it will be a constant. So I can denote it with B sine kx. Okay, if you notice this one, so this one, V, it depends on x as well as on t. Okay, so we can easily write this one as Vxt. Okay, but I'm just using V. Okay, that way it is simpler for me. But always remember that if you have to write it fully, it will be Vxt. Okay, so this is a solution. Okay, it is a general solution and it contains two constants. Now we need to find out the value of these constants A and B. How will we do that? Okay, so this no longer depends on the initial conditions. Okay, because this is after the experiment has taken place again. Okay, so you cannot use the initial conditions for V. Okay, but after the experiment has taken place again, we can still use the boundary conditions because the boundary conditions hold after the experiment has taken place again. Okay, so now we can use the boundary conditions. Okay, let me just write it down. Okay, so we were having that the boundary conditions was u0t equal 30 and u-lt it's equal to 100. Okay, so these were the boundary conditions for u. Okay, but now we are having v. So what we will do now is we will find the boundary conditions for v. Okay, which I will do here. Okay, so this part over here is reserved for finding the boundary conditions for v. But how exactly do we do that? If you remember, we had written v equal, we had written u equal v plus uf. So that is exactly how we will find these boundary conditions. So we can write u minus uf, and uf you can replace it with this portion here. U I will keep it as it is, and uf will be 70 by L x minus 30. Okay, so now let us find the boundary conditions. Okay, when v at the boundaries, that is when x is 0, time is anything. So it will be u0t, okay, minus 70, and x will be 0 because the position is at 0. So this part will be equal to 0, minus 0, minus 30, and u0t, it was 30. So now it has become 0. And now let us also find for the right boundary, VLT. Again, it will be ULT. Now over here will be 70L by L minus 30, and ULT is equal to 100 minus, okay, minus 100. Okay, if you simplify, will be 0. Okay, surprise, surprise. Now the boundary conditions for V, it's equal, they are both equal to 0. So now we are having homogeneous boundary conditions. Okay, so after having homogeneous boundary conditions, we can now use them over here for the solution of V. Okay, to find out the constants. Okay, let's see. Let us do that. Let us first use the first boundary equation. Okay, what can I do? Okay, I can erase this one. Okay, but let me just note it down somewhere. Okay, I may need them again. Okay. So we were having that V, it's equal to A cos kx plus B sin kx E minus alpha square k square t. Okay, we were having that. And we were having these boundary conditions. So what we will do, okay, we can substitute x equal to 0. If we substitute x equal to 0, what will happen? Okay, when x is 0. When x is 0, use this boundary condition. So V, it will be equal to 0. Substitute it over here, x equal to 0, V is 0. So you will be having A cos 0, which is 1. B sin 0, which is 0. E minus alpha square k square. Okay, so over here, this boundary conditions work for any time. Okay, so in fact, it can work for when time is equal to any seconds. Okay, you can just put it anywhere, and you will be seeing that this one won't be equal to 0 unless time tends to infinity. Okay, so you will be having that A will be equal to 0. So we have found out the value of A. We can substitute it over here. So we will be having V, it will be equal to B sin kx E minus alpha square k square t. So we'll be having this. We have used this boundary condition. Now let us use this second boundary condition. Now V is L. Now using the second boundary condition, 0 and x equal L. When x equal L, V is equal to 0. B sin KL. Okay, and over here we'll be having this. So if you notice this one, this part won't be equal to 0. So you will be having this B equal to 0 or sin KL equal to 0. Okay, but if B is equal to 0, if B equal to 0, what will we be getting? We will be getting that V will be equal to 0 because A is 0. Now B is also 0, so V, it will always be equal to 0. Now just think for a moment, is that even possible? Okay, does that really happen? For any time t, we are saying that V will always be equal to 0. It cannot happen, right? It's of course a 0 solution. Okay, but let us find out some other solutions. Okay, so what we are interested in is sin KL equal to 0. Okay, so I can write, okay, I was using the capital letter, sin KL equal to 0, which gives us that KL equal n pi, which ultimately gives us that K will be equal to n pi by L. Okay, so we have used the boundary conditions, we have used the initial conditions. Okay, now what we will do is substitute K over here. Hence, V equal to B sin KL E minus alpha square K, which is n pi by L. Okay. Okay. So K, it is n pi by L, so you will be having n pi x by L substituted here, and K square will be n pi by L whole thing squared E. So you will be having this. Now, how many solutions are we having over here? We are having infinitely many solutions, because this solutions works when n is equal to 1, n equal to, and so on. So what we will do now, instead of writing it as V, we can easily write it as Vn. And over here, Bn. Okay, because we are having infinitely many solutions. Now, what will we do? After finding these many solutions, we can now use the superposition principle. Okay, because we still haven't found out what Bn is. Okay, so now let us use the superposition principle. If this one is a solution of that diffusion equation, okay, del 2V. Okay, remember that we had to replace it with V, del V del T. So if this is a solution, even if you take a linear combination of this, of these solutions, it will still be a solution. So what can we do? We will take V equal to a linear combination, that is sum all of these. Sine n pi x by L E alpha square n square pi square by L square T. So we can take V to be equal this. Next, what will we do? We are interested in finding U. Okay, so again we will write U. It is equal to V. Okay, so U equal V plus UF. So remember that we had found out V equal to this one. Okay, I will write it. And UF, if you remember, we had found out to be this. Okay, so we are still interested in finding Bn. Of course, we have found out partially what U is. Okay, but we want particular solution. Okay, what will be Bn? How do we do that? Remember that when we were talking, we say that this one is uxt and this one is vxt. This works for any time. So even if t is equal to 0, it will work, right? So even if t is 0, it will work. So when t is equal to 0, u it will be equal to ux0, right? Because it is uxt, but ux0 we had written it as u0 or u0. So u0 will be equal to n. Okay, this whole thing. And e power 0, e power t will be 1. Okay, and over here 70 by lx plus 30. But remember what u0 is. U0, remember we had found out that it was 40 plus 10. So what can we do now? Okay, we can take all these things to this side and then we can use Fourier series. Okay, so now we can take everything. So we'll be having minus 30x by L minus 20. Okay, use Fourier series. And then you will be finding Bn. Okay, so that one Okay, maybe I can do it in a separate video, but I hope that you are familiar from this step onwards, and then substitute again Bn, or just write the expression for this one again. You will be having the final solution. The final solution is indeed U, okay, but after finding Bn. I hope that is clear. Until next time.